Goodness. So for those that are online, please just voice up if you have any questions, just because I'm not able to see the screen. Sure. And for those that are online, are you able to see the page?
Yes.
Yep.
Yes.
Okay, I think I figured out that volume. Wow, that was loud. Okay, great, thanks. Okay, so questions. Anybody have any questions? First thing I'll address is no, I did not get material on the Canvas page. So I'm sorry, it was a crazy day yesterday. So I was able to get a couple things on there this morning. So there's separation of variable material and there's capacitor material. I will get everything by the end of this week on there, so you'll be ready for an assessment on Monday. As far as kind of a review, the goal of a capacitor. The right angle. Okay. Is to understand first kind of what is a capacitor. So what does a capacitor do? So that's the first goal. Anybody want to voice what a capacitor does? Okay. Stores and releases energy, which you can visualize as what? What kind of a component can you visualize it as? Yep, great. Okay, so that's the first thing that you kind of have to understand is it stores and releases energy. Sorry, can't write today, I guess. There we go, energy. So think of it like a battery. Another way you can visualize this is a voltage source. So, you know, battery looks like a voltage source. So that would be kind of the component that we can think of this like is a voltage source. I had mentioned last time that you need to memorize the relationship between current and voltage. And what is that for the, anybody remember that one? It's what? So that's the discharge and charging. So that's the time constant. So that is correct for the time constant. The relationship though between the current and the voltage. So sort of like Ohm's law.
So the current isn't it the capacitance times by the voltage transposed to time?
Correct.
Okay.
Yep, that is the relationship. So this is the equation you have to memorize. One of them, the other one is the 63%. So the other thing to know about this is that the current's going to be time dependent and the voltage is going to be time dependent. And I know last time a person had a question here like, well, what do I know is like my known values and what am I trying to solve for? So in most of these cases, we're trying to get the equations that are describing this. So the current or the voltage would be what we're trying to achieve in these. So those are usually the goal of what we're trying to find. And then like the capacitor, resistor, voltage source, those would be your constants that would be in there. So in this case, that C would be a known value of capacitance. Okay, so that's for the capacitor. Inductor. It stores and releases what? Or what can you think of it as? Yep, current source, good job. Okay, so this one, you're gonna have the component is a current source. And the equation that you have to memorize for this one relating current and voltage. Back and look at the notes. Go ahead.
That voltage or VT equals inductor L times the I.
Correct. I'm sorry, this was the VC and the current IC. So in this case, again, the voltage and current are time dependent. So they're what you're trying to solve for. And L would be a known value. So the inductor is a little bit harder to understand the storage and release. And so usually just thinking of it as like a current source may be better. So I'm not going to put anything else there. I think that's probably sufficient. Okay, so those are the first two concepts, like you need to understand these concepts. And then we started talking about RC and RL, where we've added in a resistor. So for RC and RL, so for these kind of circuits, we went through the derivation of using a first order differential equation. And I showed you how to do the separation of variables. So that's that technique that I described there was called separation of variables. Some of you may have seen that in math, and some of you may not yet have seen that in math. So if you haven't seen that yet, you'll see it. It's not a super hard concept, but it's a little bit different than what you've envisioned before, because you have to take that di dt or dil of t and look at that as kind of its own quantity and dt separately. And so that's what's kind of confusing to see it. So for this one, we got an equation. So for this, we were able to derive and notice that for both quantities or for both circuits, the end equation was very similar. For an RC, it was a description of current, and the general form was a final value plus an initial value minus the final value. E raised to the minus T0, where T0 was kind of a starting time over tau. And tau for this was our Thevenin times C. And then Edison had said already, the 63% was when we figure it is charged or discharged. And so that would be where we would say, yeah, we consider that charged at 63% of the final value, or it's always 63% of the final value. So if it's charging, it would be 63%. If it's charging up to 10 volts, it would be 63% of 10. So at 6.3, you would be saying that, okay, I consider myself actually charged. And then if it's discharging, you would say, okay, at 63% back to 0 is where I'm considering myself discharged. And so those would be the time constant. So that 63% of the final value is where we consider it charged or discharged. Okay. And then for the RL, Same color. You're actually going to have the same equation. It's just this time it's going to be VL of T. So it's going to be the final plus the initial minus the final, e to the minus T0 over tau. And in this case, tau is L over RTH. Sorry, these are backwards. VC, oh my goodness, yeah, I'm tired. This is L over RTH, and this is IL. I have these backwards. Okay, VC and IL of T. So they're the same form of that final initial minus final, e to the minus T0 over tau. And hopefully now you understand where these equations came from using that separation of variables and derivation. So instead of having to derive this every single time, we want to find this a lot quicker because took a lot of time to derive that, right? So there is a way to get this equation by just looking at the circuit. So we're going to look at that today. So that's where we're going in this is let's try to get the descriptions of these equations. And so what would we need to know to be able to write this equation? Okay, so we need to know RTH would be one of them. And we would need to know VTH will be in there in the equation somewhere. So we would need to know the Thevenin. What else do we need to know here? Correct. So we need to know final value, initial value. And so that's where we're going to start. So this is written out in a little bit different way than I just said, but it's initial minus final. And then this is the final value. Okay, so first step is to find RTH. You're going to remove this capacitor or inductor from the circuit and then find that Thevenin resistance. Where you're putting, you remember when you did Thevenin, you found like between A and B. So you had those A and B locations. The A and B location is going to be wherever your capacitors, sides of the capacitor are, or the inductor sides of the capacitor. So you remove out the inductor or capacitor and put A and B locations there. And then you find the Thevenin equivalent from that location as A and B. So then we're going to look at, this will be your initial time. And you're going to say, okay, it's been sitting at this position for a really long time. And then that is going to cause the differential equations to go to zero. So dVc dt goes to zero. So the capacitor, remember, looks like an open. And then dL dt goes to zero. So that means that the voltage is zero. So it looks like a wire. So we're going to replace those with a wire or an open. And then we're going to analyze that circuit to solve for the current or voltage. And then across the capacitor or through the inductor for the current. So that gives us those initial values. And then we're going to set it. So this step here is that we are going to set it to, so right before something happens, we're going to find the values. And then right after something happens, we're going to use that the capacitor looks like a battery and the current or the inductor looks like a current source. So we can use those two elements and then solve for any voltage or current in that circuit. And that would be our actual initial value for other areas of the circuit. And then at a final value, so this is going to be final, you're going to do, again, the circuit has become stable again, so it's either open or a wire for the inductor. And we're going to analyze those circuits. So each time you're going to redraw the circuit for these different configurations. So let's look at an example. So after being open for a long time, the switch is closed at t equals 0, and we want to write an expression for the voltage VC of t. So I like to, you can start with tau, but I actually like to start with the initial value. So I'm going to redraw this circuit now with initial. And I'm going to assume that the switch, I've determined what the switch location is and what I do with the time dependent element. So that's the two components that I redraw everything, but I need to decide on those two factors. So after being open for a long time would be the initial time. So I draw it in an open position for the switch. So that helps me determine where do I put the switch. And so this will be just an open here. And then what do we do with the capacitor after it's been sitting for a long time? Correct. So it's also going to be open here. So I label the VC of t the same. So this is going to be VC of 0 minus, meaning before the switch happens. So that's what the 0 minus means. And the 0 plus would be after the switch is moved. So that's going to be my initial value for VC. And so I noticed here that that is the same. Green. It's not very big. Okay. So this is all the same wire. And this is all the same wire. So that VC of 0 minus is the voltage across that 30K. Can you see that visually? So remember again, if color coding helps you, get your colors, mark those extraordinary nodes so that you can determine where that voltage is. After a while, it will start to be more second nature, but again, you guys are just kind of still beginning. So how am I going to solve for the voltage across that resistor? Correct. So I times 30K, and what do I notice about I? So I is going to be the current here. And that would then be the same current, right? Which is also the same current. So what is I? Hearing somebody saying it, to say it a little louder. Correct. So it's going to be 120 micro times 30K. Which, wherever that is. Do you have it? I have the right one up. So what is it? 3.6 volts. Yeah. Thank you. All right, so this is our, what we would consider our initial value, because right after the switch closes, that VC has got to be the same, right? So VC of 0 minus has to equal VC of 0 plus. If I was solving for a different element in the circuit, I would need to redraw again and use a voltage source for that capacitor. And then I would solve that, and that would be the initial value. But for now, we'll just stick with just the capacitor and just the inductor and go through these examples. Okay, so this is my initial value. Okay, now I need to find my final value. So I redraw the circuit and determine what do I do with the switch and what do I do with the capacitor. So now the switch is closed for the final. So what do I do right here? Just connect them, right? Good job. Okay. Not too hard. And what do I do over here for the capacitor? Just leave it open again. And then this time it will be same polarity, plus to minus VC. And then this is now considered my final, which I use the notation of infinite as final. So now we're going to analyze this circuit. And again, it's the voltage across the 30K. So again, this is the same. And this top is the same. So it's going to be, again, the voltage across the 30K. So same idea. I can do I times 30K. We'll do I2 this time. I'll call this one I1, just so they're not confused. So I2 goes through the 20K. But now there's an extraordinary node here instead, right? So there is, I2 is not 120 micro this time. Does this circuit look familiar? Yeah. Correct, it's a current divider. So we can use the current divider equation. Or if you don't remember that it's a current divider, how else would you solve this? Do what? You could do source transformation and then do a voltage divider. That would work. I tend to make errors on source transformation, so I typically don't use source transformation. Any other ways we could solve this? Do what? Thought I heard somebody say. ECE. Okay, so we can do, there's two loops there, so you could do 2 KCL or KVL and then a KCL. So it'd be two loops and then a current summation. Any other ways we could solve it?
Could you swap the current source and the so they're both while they're still in parallel?
So you could combine the 10K, you notice, is in parallel with the 120 micro, and then it's in parallel with 20K plus. So you could combine both resistors branches as one, and then that would find the voltage across the 20 and the 30, and then you could do a voltage divider that way. So there's several different techniques here you can do, and you can use all of them should get you to the same answer. So the little bit of a shorter step than doing 2 full loops and a KCL would be to use node voltage, which kind of combines them together as one. And so you could also use node voltage on this. And so I would call this like V1. And so my node voltage equation here would be what for this current branch would be. What would be the description for that one?
U1 minus -0.
Correct. And then this one. Correct. And then this one. Yep.
So it's the U1 over
It'd be V1 minus 0 over 50K. And so then I can combine the V1s. For 10K. And then if I know V1, what's I2? So since I don't know V2, instead of adding in a V2 right there, I could just do this. This has been acting as my ground. And I2 goes through the 20K and the 30K. So it'd be easier just to use Ohm's law of the V1 minus 0 over 50K. Does that make sense? Okay, because that way, I mean, yes, you were right, but you don't know what that kind of have to label this V2 node, and then you would have another unknown. So instead of that, trying to see like, do I have another known? And yes, you have that ground. So then V1 over 50K. So rewriting this ends up giving me what I would have gotten from the current divider equation. And let's see what I actually have for this value. Okay, so this ends up giving me a value of 0.4 volts. So this will be my final value. So I now have the initial value, final value, and all I'm missing is tau. So for tau, I like to do it at the final value stage. So that final value stage was, this was closed again. And now because I'm just trying to find the Thevenin for this, which is the goal of RTH you need to find for tau. Where the element is for the capacitor, I'm at the A and the B locations. This would be my A and my B. And I look at this and I only have independent sources here. So for a Thevenin, the easiest way to find a Thevenin is just to reduce down the sources. If it's a current source, it will become an open. If it's a voltage source, it will become a closed. And then just take the pathway from A and then take the pathway, oh, you can't see that at all. And take it around to B, and that will be your Thevenin. So here I'm going to open this. So that becomes an open. And my pathway now, I want to go through this, and I see, as I take my pathway through here, I see that this splits, which means it's a parallel form. So I'm going to have a parallel branch here and here, and combining the 20K. And then I see that this section here is in series. So here, those two become in series. So I can add those two together. And then as I come through here again, it splits again to combine them. So everything in the blue branch would be added together because they're in series. So I have 30K. And then that is in parallel with the 30K. So that is my RTH, and that ends up being 15K. And the capacitor value was given as 10 nanofarads. So tau is going to just be 15K times 10 nanofarad. This is in ohms, which gives you actually the seconds. And this ends up being 150 microseconds. So now I can write the equation because I have all the components to it. Yeah.
Oh,
Yeah, it's small in there, but yes. So that was a given value, yes. I just magically like created that. Yes, so remember capacitors, resistors are given values, and inductors if we're doing an inductor. So now I can write this. And so VC of T for time greater than 0, meaning that the switch happens at 0. So that would be the description, is the final time, which is what value? Yep, so 0.4 plus, this is going to be my initial minus final. So my initial value was 3.6, and then minus 0.4 for the final again. E to the minus T0 in this case is 0. So note that too. T0 for this is 0. So it's just minus T over tau, which is 150 microseconds. And all of this will be volts. So then I can simplify it slightly to 0.4 plus, oh wait. Yeah, 3.2 e to the minus T over 150 micro. And all this is in volts. And so that would be my answer. This is simpler than deriving the whole equation. So we had to understand though where the equation came from so that we can say like, okay, these are now what we need to do to the circuit to be able to get those values. All right, questions? Yes.
Why do we distinguish between T of 0 from the negative and positive side? Because like capacitors resist voltage, right? So they're the same. Like, why do we care to use?
Yep. So that is because
So 5, 3, 7.
there we go. Okay. So all right, so if in this case, whoa, big line. So for you guys that are online, so that you probably can't hear as well, he asked why we specified this 0 minus and this 0 plus here. So because we are solving for the VC, it's going to be equal. So those values are going to equal each other. But if we were not using the VC of T and we wanted to find, say, the voltage across this component here, V of T, then we would do one more step in this. And we would need to find, this is my actually initial value. So in this case, if I wanted to find V of this one to be the initial value, so this would be 0 plus. I would have to redraw this circuit. So any other current or voltage in this circuit, I can still find this and describe it by these equations. The extra step here is that here I have to replace it now with a voltage source of that initial value that we found for the capacitor, because the capacitor is the only element that can't change instantaneously. A resistor can change instantaneously depending on what voltage I put on it, right? So like if I put a 5-volt battery, it's immediately going to have the current going through it of whatever the 5 over R. And if I put a 10-volt, immediately it's a new current value. So it can change instantaneously, but the capacitor cannot. So we have to use that characteristic to solve for any other voltage or current in the circuit. So now I could get this V 0 plus, which would be the actual initial value for its equation. And so I would do the current times this, so it'd be 120 micro times 20K, and that would be actually its initial value. Does that make sense?
Yeah, for the resistor.
Yeah, so this would be just for this component here.
Okay, so this method applies to RC surveys, so we're just lucky that we're only asking about the capacity.
Yep, so we don't have to do that extra step because we know that they're already equal. Otherwise, you would need to do this extra step. And we'll do more examples like this, but it's just one more step complicated. So I was just starting with the easier one first. Yes.
So is T 0 plus the moment of the switch?
Yep. So it would be, oh, yeah, sorry, this, you're right. This would actually be right after the switch closes. So this would be closed here. But this is not the accurate value for initial. So I would do node voltage again here. We'll call it the V2. Thanks for catching that. So yes, the initial is actually just right after the switch has changed. And then you use the capacitor factor of the initial value we just found. So that 3.6 volts. So you would redraw it for this circuit and then solve for that V of 0 plus. So this is going to be V2 minus 3.6. So if you remember from so I labeled this V0 plus as a plus to minus. And remember for voltages, if I'm trying to find a differential voltage between this place and this place, if I know those two voltages, then I can find the difference. So if this is Vx, this is 10 volts, and this is 8 volts, what's Vx? 2, right? So it's just the right side minus the left side. So remember, that's the differences. And so I just take the right side minus the left side. And so this is the same idea, V2 minus this voltage, which is 3.6 volts. So then I just need to find V2 here. And V2 over 10, K minus 120 micro. Oh, there you go. So I have this current. What is the current going through this one going to be described as? What's this voltage here? It's 3.6 volts, right? So what's the current? Oops. So this current? Correct. So V2 minus 3.6 over 20K. And then that's all three of those branches out of that node. And so that's my node voltage equation. I can solve for V2 there, plug it in, that would give me that V0 plus.
I got just using V0 plus right here.
Uh-huh.
It's like, I understood like we were doing this. And they were switching it on.
Right at the time that the switch changes. So we're doing it like right before the switch, that's 0 minus. And so that's why we have the first one is open. And then we're doing it right as the switch closes is the initial condition. Does that make sense?
Yeah, so we're just saying like if the switch is closed.
Yeah, right immediately as it closes, not when it's closed and sat there for a really long time. So right when it closes is that initial time for anything else in the circuit. But because before when we closed it, the voltage across the capacitor has to stay exactly the same. So that's why that gave us that value of 3.6 in the previous question. So this is kind of a separate question. So now we can actually write we have to do one more step, but we could write the equation for this one. So your tau is going to stay the same for both for any element that's in the circuit. Grab another. The other thing that's going to be different for this one is the final value. So the final value for this one where this switch is closed and then this one's still open. But now we want to find the final value across the 20K. So this example is that we're writing an expression for V of t here for t greater than 0. So this ends up being minus 1.6 is this value here. So this is going to be our initial value. This is the initial for the capacitor. So negative 1.6 will be our initial value, and then we need to find the final value. So how can we find the voltage across this 20K? Okay, if we knew the voltage here, right? We could do a voltage divider. You could do a current divider and then just use the current and do I times R there. So that would be another way. Any other thoughts? How else you could solve this? You're going to see my favorite way is always the same.
Combine the two into series.
Correct. Or a voltage divider again. So yeah, if you combine the 10K and then the 50K in parallel, then you could find the current going through both of them and do I times R and get the voltage. I'll call that V3. And then do a voltage divider there. So my favorite is node voltage. So that would be the other way you could solve it. So any of those methods would work, whatever you're most comfortable with. So I'll show you mine because I like to use node voltage. So using node voltage, you would have V3 over 10K would be this branch. What would be this one? Yep, minus 120 micro. And then this branch. V3 over 50K. And then I would solve for V3. And then divide that. And then from here, I would do a voltage divider. And so V final here would be V3 times 20K over 50K. And that value ends up being so this ends up being V3 ends up being 1 volt. And this one ends up being 0.4. So I think I made an error on the first one. This might not be 0.4 here. Somebody wants to plug in those numbers. It's 0.6. Thank you. Okay, sorry. I will go back and change this to 0.6. So I just realized I miswrote that. Okay, so that's 0.6. You guys want to go back and change that? So 0.6. So this one down here will be slightly different. 0.6 will be your final, 0.6, and then 0.6 plus 3.0. So again, that VC at final value is actually 0.6 volts. Thank you. And then the final equation will be 0.6 plus 3.6 minus 0.6. And then that reduces down to 0.6 plus 3. And then here you're going to have the equation is going to be, again, final plus initial minus final. E to the minus t over tau. And tau will be the same, so that never changes for your circuit. And so what's our final value here? 0.4. And then initial minus final. We're going to use that minus 1.6 for the initial. So minus 1.6 plus 0.4 e to the minus t over 150 micro. And so we've been able to actually get the voltage across that 20K resistor for this. All right. Any questions? You guys ready to tackle one on your own? No? Yes? Yes, question.
The distinction between t equals 0 minus and t plus that, because capacitor voltage doesn't change instantaneously. So the capacitor voltage at t 0 minus and t plus is equal.
Correct.
But if we're analyzing a node separate from the capacitor itself, that's where that distinction becomes. Is that correct?
Correct. Yes.
Okay.
So yes, that was a good iteration. So in the first example we didn't have to do this extra step here where we flip the switch right at 0 plus, because we know that it can't change instantaneously at that capacitor. So because it can't change right away, that is our same value. So we don't have to go through that extra step. But here we do, because the initial value is actually right as the switch is switched. The switch changes positions. All right, any other questions? Okay, you guys are going to work in small groups and try to come up with the equation for V1 of t here. So again, introduce yourselves to your neighbors. All right, for you guys that are online, if you guys want to, I think you can annotate. Might be able to annotate on this, or if you want to just take a picture. I'm going to put you guys in a breakout room. Oh, maybe I cannot. Oh, let's see. Breakout room.
Oh, yeah, sorry.
Give me a second. I'm gonna figure out how to put you guys in breakout room.
Right, you guys all want to go into the breakout room, and then you guys can work as a group together and try and solve that equation. So we have like feedback going on here, sorry. Keep that for a second.